So who wants to win themselves a Mavic Pro drone? I will be giving one of these away as a prize to the person who successfully completes this challenge. Now, anyone who has followed my channel for a while knows that the Equinox and Equatorial Mounts are two of my favorite topics because they are very clear evidence that the Earth cannot be flat. And that is what this challenge relates to, because I regularly get comments from flat earthers on my telescope videos and on my Equinox videos claiming that it works just fine on a flat Earth. Now, the geometry of the Equatorial Mount cannot work on any flat surface, and the geometry of the Equinox Sun angles cannot work on a flat Earth. However, this challenge is going out to flat earthers to prove me wrong. If you can model successfully a flat Earth that demonstrates the Equinox Sun angles and the operation of Equatorial Mounts, you will win yourself this Mavic Pro drone. So let's have a look at the details. So let's take a look at the challenge, the Flat Earth challenge. There are two questions that we need to answer. Number one, can flat Earth explain the Equinox Sun angles? And two, can flat Earth explain the operation of Equatorial Mounts? So looking at some real observations anyone can make on the equinox is that 1, except for the north and the south pole, the sun rises due east 090 degrees all over the Earth. 2, except for the north and the south poles, the sun sets due west 270 degrees all over the Earth. 3, at local noon, 90 minus the angle of the sun above the horizon will match your latitude. 4, the length of day is the same all over the Earth. And 5, the sun moves in a straight line from sunrise to sunset if you are positioned on the equator. Looking at the Equatorial Mounts, number one axis of the mount is polar aligned, and that means it is aligned directly north and south geographically and elevated to an angle equal to the latitude of the location. Now, if you're in the northern hemisphere, the angle is upwards towards the north. If you're in the southern hemisphere, the angle is upwards towards the south. So that is how they are operated in the real world. Number 2, they can track stars and the sun using a single axis of rotation, and that axis that rotates is the one that is polar aligned. The rate of rotation is the sidereal rate when you're looking at stars, and that is 23 hours, 56 minutes and 4 seconds for it to do a complete revolution. If we are tracking the sun, the mount will use the solar rate, which is 360 degrees in 24 hours. And number 3, importantly, they work all over the Earth. If you're in Alaska, if you're at the bottom of South America, and you have your equatorial mount correctly polar aligned, it will be able to track the stars and the sun using a single axis of rotation. So let's take a look at the contest rules. You must use a real model with a single real light source. No CGI. There's no point producing an entry with CGI because it will not be a valid entry. It must be a real physical model, and that model must demonstrate the following. 1, 090 degrees east sunrise all over the Earth on the equinox. 2, 270 degrees west sunset all over the Earth on the equinox. 3, the angle of the sun from vertical matches the latitude at local noon. So that's the same as what we discussed earlier, that the angle of the sun from the horizon subtracted from 90 will match the latitude. The other way to look at it is the angle of the sun from vertical matches the latitude at local noon. Number 4, daylight and darkness period is equal all over the Earth for 24 hours. So your model using that single light source must demonstrate that for any position on that Earth, the period of daylight and darkness is equal across a 24-hour period. Viewed from the equator, the single real light source must appear to move in a straight line from sunrise to sunset. Your model must show continents and oceans in approximately the correct relative positions. Okay, now I don't need to be too precise with that. I simply want the correct oceans in the correct relevant positions to the continents. So the Pacific Ocean, for example, on the east coast of Australia, the Indian Ocean on the west coast of Australia. So you need to produce some continents and oceans that match reality. You must use a single light source. Number 8, demonstrate how an equatorial mount that is polar aligned, that is aligned north-south and elevated at the same angle for latitude, can track this single light source with a single axis of rotation from any location on Earth. Now I know this might sound like a very difficult task, however, all of these observations can be made in the real world, and furthermore, they can all easily be demonstrated on a model using a globe. So because this is a challenge to flat earthers, the entries must use a flat or nearly flat surface for the shape of the Earth. It can be whatever shape you want, a diamond, a triangle, a circle, it does not matter, but the surface must be flat or nearly flat for this entry to be valid. So even though this challenge is for flat earthers, to prove that the Equinox and Equatorial Mounts can work on a flat Earth, I don't want you to feel left out. This particular contest will run until the 21st of March 2018, which is the next equinox. The first entry that satisfies all the rules of this challenge wins the drone. If there are no successful entries by the closing date, the contest will be expanded to include entries based on the globe model. I will announce that in a separate video on March the 21st. From that point, the first globe-based entry satisfying all the rules listed above will win the drone. So good luck and let the real Earth win.